I will be talking to you about some work I've been doing over the last kind of many years now. I generally work on data that are not independent or identically distributed. I work a lot on spatial causal inference. So in what I will be talking to you today, I don't want you to think of any of the variables as independent across units. And all the random variables that I will be talking about today have some spatial structure, in the sense that observations that are nearby in space have more similar values than observations that are further away in space. Now, that can be problematic in some settings, but in the settings that I will talk to you today, they can be useful in relaxing the non-measured confounding assumption, I believe. So this is work that spreads 2 papers with Corey Ziegler, Christine Chouara, and Patrick Schnau. All right, but before I talk to you about unmeasured spatial confounding, I want to talk about a little bit about the term spatial confounding. And that's because in the spatial statistics literature and in the causal literature, this term is used to represent 2 completely different notions. So in spatial statistics, the goal will be different than what it is in causal inference. So we have to be careful about when we talk to people that are in different parts of the statistics world about making sure that we have the same language when we talk to them. Now, in everything that I will be talking to you today, I will be using Z to represent a treatment. I live in the potential outcomes world. So YIZ will be the outcome observed for location I, had they been exposed to treatment Z. The measured outcome will be assumed to satisfy the consistency assumption. And we also have a vector of measured covariates C. Now, in spatial statistics, what spatial statisticians often want to know is the relationship between an exposure and an outcome. And often what they care about is understanding the relationship between your exposure Z with the outcome Y, conditional on their measured variables. Now, if you had, remember everything is spatial, so if you have Z, Y, and C, and you fit this regression model, a lot of times the residuals you'll get from this regression will be spatially correlated. So if you do this, then your assumption that the residuals are independent is violated. And spatial statisticians, of course, don't like that because they want to make inference on their coefficient. So often what they do is that they include a spatial random effect in that regression with the idea that that spatial random effect is going to absorb all of the spatial correlation in the residuals. And now their inference on the coefficient of the exposure will be correct. But what happens in reality is that because this spatial random effect has a spatial structure and your exposure also has a spatial structure, these end up being collinear. So the coefficient of Z in a regression with a random effect and without a random effect does not have the same interpretation. So this is what in spatial statistics they use to, they think when they talk about spatial confounding. Their goal of estimation is the conditional relationship between Y and Z given C. And when they put the spatial random effect in there, that acts as a confounder in that it blurs the relationship between Y and C, given the measured covariates. Now, there's literature in spatial statistics that discusses this problem. Now, in causal inference, though, we have a kind of like different notion of spatial confounding. So for us, what confounding is, it essentially means that we have to adjust for some variables if we want to estimate a causal effect. So what that means here in the way that I like to think about spatial confounding is that, in fact, the relationship that we want to learn is a conditional relationship between Z and Y when we condition on some variables L that satisfy the classic non-measured confounding assumption. But these random variables L include the measured variables, but also necessarily need to include some unmeasured spatial variables as well. So there is this spatial random variable U that is a confounder of the Z-Y relationship, and we need to adjust for it if we want to estimate causal effects. So this is a kind of like a crucial difference between spatial statistics and causal inference. So if you want to estimate, essentially, if you want to learn the causal effect of Z on Y, you need to condition on all of the confounders, but you don't have access to all of them. You only have access to a subset of them, C. So what you can do, well, the first thing you can do is you can try to fit this this model that doesn't adjust for the spatial confounder at all. And because it doesn't account for all of the confounders, this will not give you something with a causal interpretation. But also, if we borrow from the spatial literature and we try to include a spatial random effect in this regression model, this spatial random effect, it cannot learn. It's different. This U here will be different from the actual confounder. This will be used to essentially try to absorb the spatial correlation and the residuals, but it won't be the confounder of the ZY relationship. So none of those two models can actually learn the causal effect of interest. And we need to actually have the unmeasured confounder U if we want to actually estimate the causal effect. So I wanted to start with this because I don't know, I know this is a causal inference group, so I know that perhaps spatial confounding is a term you haven't heard before. But a lot of times when I talk to people that have exposure to spatial statistics, the thing of spatial confounding is a completely different thing than what I think spatial confounding is. So spatial statistics and causal inference, when they talk about spatial confounding, they have these two completely different notions. But the common thread is that in both of these literatures, we talk about confounding as something that blurs the relationship that we want to estimate. It's just that for us, an unmeasured spatial confounder is something that we need to explicitly adjust for if we want to estimate causal effects. Now, if that unmeasured confounder does not have any structure, so if we had IID data, we need to, there's not much necessarily that we can do there. This is up for debate, at least not without assumptions. But here I want to talk to you about the situation where this unmeasured variable has this spatial structure and how we can actually use that spatial structure information to learn that unmeasured variable and adjust for it. So these types of problems, I have been working on kind of different applications, but one of the application areas that I've been working on a lot is air pollution epidemiology. Now, in air pollution, there's been a variety of regulations that have taken effect over the last few decades in the United States to reduce air pollution from various sources, power plants being one of them. Power plants can follow different strategies to reduce emissions, and one of them is to install these SCR and SNCR systems on their smokestacks. So essentially, you have a power plant, it emits this really dirty air, they put a filter there to make the emissions a little bit cleaner. So the idea is that these SCRs and CR systems, they reduce NOx emissions. And because NOx emissions are a precursor of ozone, the idea is that because NOx emissions go down, ambient ozone concentrations will also go down. So we want, though, to use data to evaluate this relationship. And in air pollution epidemiology, most of the random variables we deal with are spatial in nature. So here I'm just showing you PM2.5 concentrations across the New England. And there's this spatial trend in the sense that, again, nearby observations have more similar values of pollution than not. So we also expect that the confounders of this relationship might be spatial in nature. So this is the situation that I'll be talking to you later, where the treatment is binary, and there might be unmeasured spatial variables. We have another application where the treatment here is continuous. You can take values from 0 to 100. And it represents the percentage of a population in a county that doesn't have access to supermarkets. And the belief is that if you don't have access to supermarkets, you don't have healthy eating habits, and that might lead to subsequent problems with your cardiovascular health. And here again, potential confounders can be a number of different things, but they generally are expected to be spatial in nature. So I'll be talking to you, well, depending on time, on how we can address how I think spatial information and the fact that we can assume that these confounders are spatial can help us adjust for them. Now, in the first case with the binary treatment, we are extending propensity score matching to what we call distance-adjusted propensity score matching. So our estimate of interest is the average treatment effect on the treated that represents how much the treatment changed the outcome among those that actually received it. Now, if we want to estimate something like the ATT, and I'm sure I'm talking to you, so this is great, I could go really fast. If all of your confounders were measured, you could estimate a propensity score match on that propensity score. But now, not all of the confounders are measured. We also have some that are unmeasured, and we also want to adjust for them. So the idea here is that, okay, you can estimate something like a proxy propensity score that has the measured covariates, and that propensity score will balance, essentially, you can think about it this way, or will bring the measured covariates of treated and control pairs closer together. But you also want to bring you also want matches of treated and control units that are nearby in space, because they're also nearby in space, that unmeasured spatial variable will also have similar values. So we combine propensity score difference and spatial proximity essentially in one measure that is called the distance adjusted propensity score. So when we have a treated unit I and a control unit J with a small value of DAPS, that will mean that their propensity scores will be similar, and and the treated and control unit will be nearby in space, so their spatial confounder will also have similar values. And this parameter W controls how much weight we want to give in the measured variables compared to the unmeasured variables. So I like this little kind of like cute graph that I think it shows you that if you think of this line as being W, that weight, the larger the W is, the more weight is given on the measured variables. The smaller W is, the more weight is given on the spatial variables. So we are somewhere on this line where to choose W, we have to kind of like navigate this trade-off of how much we want to balance the measured variables versus the unmeasured variables. And I will not talk to you today about how we actually implement this, but I wanted to show you these two plots at the top that show balance of the covariates as a function of W. And the variables on the left are variables that are not expected to be spatial, and the variables on the right are spatial variables. So the spatial variables on the right, we can think that this standardized difference of means is essentially flat, irrespective of what value of W we use. So these spatial variables will be balanced either based on the propensity score or based on spatial proximity. However, for the variables on the left that don't have a spatial structure, they need a larger value of W to get balanced. So we actually see the interplay between the different values of W as a prioritization for measured and for spatial and non-spatial variables. And when we don't account for space in the matching, we see matches that can be extremely far away, but when we do account for space, we see something that is more reasonable. Now, we use DAPS, we use naive propensity score matching, naive meaning that it doesn't incorporate space, and we use a couple other approaches to estimate the effects of interest. And we saw that essentially all of the methods indicate that SCRs and CR systems reduce NOx emissions. So because they reduce NOx emissions, and because NOx is necessary for creating ozone, we would expect that reducing NOx emissions should not be leading to an increase in ozone, because that relationship would be backwards. However, the analysis that does not account for space, this naive analysis, shows that SCRs and CR systems reduce NOx emissions but increase ozone, which is backwards than what experts would expect to be true. But when space is being incorporated in all of these three methods, we actually see that even though SCRs and CR systems seem to be reducing NOx emissions, they don't seem to have an effect on ambient ozone concentrations, which is more realistic than the analysis that doesn't incorporate space. Now, this was kind of like I think that this is what you gain by assuming that the unmeasured confounder is spatial, is that somehow you can take advantage of geographic proximity to somewhat adjust for it. But that approach was somewhat causal for spatial statisticians, in that it had propensity scores, and spatial statisticians generally tend to like outcome regression. So we worked with Patrick on another paper that used outcome regression tools to adjust for unmeasured spatial confounding. Now, I will talk to you about this approach in terms of, so we assume the potential outcomes have this form, where the treatment and the measured covariates can be interacting in weird ways or in arbitrary ways, but there is no interaction between these unmeasured variables and the measured variables or the treatment. Now, this can be relaxed, but this is the framework that we considered. Now, in what follows, I'm renaming this G of W as U, and now I'm thinking of this, the contribution of all of the unmeasured variables. I don't care about what they are explicitly. All I want is that I account for that full function U. And because, even though this isn't necessary, and we have extended this in the paper today, we'll be talking to you about the situation where there are no measured variables and the relationship between the exposure and the outcome is linear. And again, that's not necessary, but this is for ease of presentation. And in this specific situation, this coefficient essentially corresponds to the treatment effect of increasing the exposure by 1 unit. All right, so if this is the case, I still don't have any data on this U or on these unmeasured variables. But if I did, and I could fit the model that regresses Y on Z and U, I could estimate the causal effect without bias. But I don't have data on U. I have just Z and Y. And again, you could have measured variables, but I don't want to complicate this for no reason. So if you have Z and Y, what you could do is you could regress Y on Z. And here again, you're not controlling for the unmeasured spatial variables, so this will be biased. You could try to incorporate a spatial random effect as what spatial statisticians would be doing. And then you would get the weighted least squares estimator here, beta tilde. And if you look at both of those and you look at the bias terms for both of these bias terms will be non-zero. And the fact that they're non-zero arises from this conditional expectation of the unmeasured variable given the treatment. So essentially, it's pretty kind of like easy thing to think about. It's to say, well, okay, here's my bias. What if I subtracted that bias term? So this part over here, without the expectation of U given Z, would be the weighted least squares beta tilde. So we subtract the bias term to make this beta overline, this affine estimator, we call it unbiased. So if we're able to identify this conditional expectation of U given Z, then we'll be able to do this bias correction due to the unmeasured spatial variable. And in general, if U is not spatial, we could never learn that. But the fact that U is spatial and it has some structure, some correlation structure across our observations means that we can take information from the exposure and the outcome model residuals and learn that conditional expectation. This is what I'm going to try to convince you in the next slide. Well, first I have to tell you what assumptions we make about the conditional relationship between U and Z to achieve that. So if we assume that U and Z are a form of multivariate normal distribution, and again, this can be conditional on covariates if you want it to be. So that so you could have a mean structure here for the Z variable that depends on measured variables. Then we parameterize the covariance matrix of U and Z in terms of its precision matrix. Well, we use the precision matrix to describe these relationships. And we make the following assumptions. First, we make a cross-Markov property assumption that says that the only value of U that matters for the exposure is the local value. That allows us to essentially, that implies that the Q matrix here, the cross precision is diagonal. We also assume that the correlation between U and Z, conditional on everything else, is constant across the locations. Now, both of those can be relaxed, but the more you relax these, the more efficiency you lose. And I am not going to talk too much about this because hopefully if I have time, I will describe them when I show you a graph. And again, I'm not going to talk too much about this, but I want to talk about where do these parameters, these spatial parameters come in? If we look at the likelihood of our data, our observed data is Z and Y. If we look at their likelihood when we integrate this unmeasured spatial confounder out, we see that in the mean structure for Y, we have this term over here that corresponds exactly to the expectation of U given Z, which is, again, this will be the term that drives the bias. So if we have this quantity over here, if we can estimate this quantity over here, which is the expectation of u given z, then we'll be able to add this back in and acquire an unbiased estimator for beta 1 for the causal effect of interest. So we want to estimate these spatial parameters, and if we know these spatial parameters, and again, G and Q are these the variance covariance of u given z and the cross relationship between u and z. Then if we can learn these parameters, then we can do the bias correction. And if we look at where the information is coming through to estimate these things, we see that the spatial structure in U leads to a spatial structure in the residuals for the exposure, and also a term over here, this G inverse, that has to do with the spatial structure of U that also manifests in the spatial residuals for the outcome model. I know that this slide is a lot, but essentially it says that if we can learn the spatial parameters for U and the relationship that U has with Z, then we can do this bias correction. And now I hope that I can give you the intuition of why we can actually do this, so instead of throwing any math in this. So imagine that you have data on a ring graph. So essentially all the spatial dependencies are represented by connections of random variables on this plot over here. So essentially UI is correlated with UI minus 1. UI plus 1 is conditional on all the values of U, or all the other values of U. UI plus 1 is independent with UI minus 1. So I want to learn the spatial parameters that drive these relationships. So rho is the conditional correlation between U and Z in the same location, and phi of U are the parameters that drive the spatial correlation of the spatial confounder. So if I can learn rho and phi of U, then I can learn some of the spatial parameters that I'm interested in. So if we look at the conditional relationship of pairs of Z that are two lags apart, so look at Zi plus 1 and Zi minus 1, conditional on Zi. If these two guys are correlated, it necessarily means that there will be some path backwards like this that drives this correlation. Because conditional on Zi minus 1, Zi, these two should be independent unless there's a spatial random variable. And that correlation has to do with rho, one phi of U, another phi of U, and another rho. If Zi plus 1 and Zi minus 1, so here they have one Zi between them. If they had two Zi's between them, so they were at distance 3 instead of at distance 2, then they would have rho, phi U, another phi U, another phi U, and rho. If they were at distance 4, they would have 2 rows and 4 phi U's. If they were at distance 5, they would have 2 rows and 5 phi U's. So essentially, by looking at how the conditional correlation of pairs of units at different lags decays, you can understand how the spatial correlation of the unmeasured spatial confounder, like what the structure of this unmeasured spatial confounder is. So we proved this for ring graphs, but we think that it can be extended to the situation where, as long as we have enough pairs at varying lags, we believe that this identifiability will also hold. And in the paper, we also show that if U is not spatial, then we cannot identify the causal effect of interest, which is not surprising, because if you don't have a spatial structure of the unmeasured confounder, then you can never learn the bias term. We use this methodology to estimate the causal effect of access to grocery stores on cardiovascular disease. And the models that did not adjust for space showed that if people have less access to supermarkets, that reduces the risk of cardiovascular issues, which is backwards of what we would expect. So it shows a protective effect of limited grocery store access. When space is accounted for either through the weighted least squares that just includes a spatial random effect, well, then we see an effect that is essentially null with a relative risk that is centered essentially at 1. When we use the affine estimator that tries to explicitly account for the unmeasured spatial variable, that effect moves a little bit to higher values than 1, but it's still not statistically significant. But at least these effect estimates are more in line with what we would expect with subject matter knowledge than not. All right, so I talked to you a little bit today about spatial statistics and causality, about how the two fields might have similar goals, but they go about it in a completely different way. I do believe that structured data, either that structure comes from spatial or network settings, it can create problems and challenges in statistics, but also it can create opportunities. And I think that this, what I presented to you today is essentially an opportunity where having structured data, where not having a random sample, but having dependencies can help us gain something instead of complicating something else. Now, the identifiability, the results we had here, they hinge on spatial correlation, they hinge on this structure, and they exploit exactly this structure. So I have the data. If you're looking for data for your projects, my data, I just generally try to make them publicly available. So yeah, these are my references, and thank you for listening.
Great, thanks. We'll take the questions during the panel session, and we have a half an hour break. And then we'll